For what we're going to do next, we're going to need to review a little bit of linear algebra. So let's start with proposition 6.4.1. This says that if A is a linear function from Rp to Rq, and let me remind you of some of the notation we use, this script L, Rp to Rq, is a shorthand for linear function from Rp to Rq. Then, and we proved this a few lectures back, there is a unique matrix M with Q rows and P columns. And we sometimes write the set of all Q by P matrices as R Q by P. This is a little bit potentially confusing notation. Our 4 by 9 is the 4 by 9 matrices. It's not the vectors with 36 entries. It's very different from our 36 or our 9 by 4 or our 6 by 6, but it's such a convenient shorthand it gets used all over mathematics, such that A of x is that our matrix times x, where for the matrix multiplication we view x as a row, as a column vector, and A of x, of course, also is a column vector. Now, what I'd like to do next is I would like to write down a couple of lemmas from linear algebra that I hope you proved, or at least you saw in your linear algebra course. The first one is that matrix multiplication is associative. You probably learned that matrix multiplication is associative, but I am going to put this in context of the linear operators that we've seen before, because in this course we mostly care about linear functions, not matrices. So let's let A be a linear function from Rp to Rq, B be a linear function from Rq to Rd, and let's let M and L be the associated matrices. Then they're matrices with the right dimension, and they are the particular matrices such that A of x is equal to M times x, B of y is not ML times y for all x in Rp, y in Rq. Then we can compose B with A because the domain of B, which is Rq, is the same as the range of A, which is Rq, and be composed with A of x. That's L times mx, and because matrix multiplication is associative, this is L times m times x for all x in Rp. So the composition of two linear operators is also a linear operator, and if you know the matrices for the two operators you're composing, you know the matrix for their composition. Here's another linear algebra lemma, which I hope you saw. I hope you all remember the determinant, or at least a little bit about it. I'm not going to write down the formula for the determinant determinant because you can find that in any linear algebra textbook, any computer or algebra software that can handle matrices at all is going to have a determinant function, and the formula for the determinant is horrible once you get to bigger than 3 by 3 or 4 by 4 matrices or 2 by 2 matrices. This says that if but here is one property of the determinant that I would like you to remember. If I've got two square matrices with the same dimension, then the determinant of their product is equal to the product of their determinants. Little bit of not terribly surprising notation here. If A is a linear operator from Rp to itself, remember if it's from Rp to itself, we don't bother writing it twice. And M is the matrix of A. Remember, there's a unique P by P matrix M such that this is true. Then we are going to say that the determinant of A, we'll just let that be the determinant of M. Then if we put all of this together, we see that if A and B are both linear transformations from Rp to itself, then the determinant of their composition, that's the determinant of the matrix of their composition, which is the determinant of the product of their matrices, which is the product of the determinants of their matrices, just turns into the determinant of A times the determinant of B. So a determinant of a composition is the product of the determinants. Now I think we've got enough notation for me to tell you where we're going with this. That is to tell you about the proposition that I hope to prove by the end of the lecture, or at least by the end of the homework today. So let's let X subset Rp be a Jordan domain. And let's let A be a linear operator from Rp to itself. Then the image of our Jordan domain under a linear translation is also a Jordan domain. And what's more, I can tell you its volume. The volume of A of X is equal to the determinant of A in absolute value, because volume, it cannot be negative and determinants can be, times the volume of X. So for the rest of this video, we'll review some more linear algebra, and then we will get started proving this proposition. Next concept I want you to recall from linear algebra is row reduction. And you can row reduce any matrix really, but we are only going to care about square matrices. If M is a square matrix, then we can row reduce M. If M is invertible, we can row reduce it to either the identity or a matrix in row reduced echelon form. And let me give you an example of how this works. We'll start with this matrix. And then our row operations, remember, you can switch two rows. There are three kinds of row operations that you can do to a matrix. The first is you can switch two rows. The second is you can multiply any row by a non-zero constant. And the third one you probably remember is you can add a constant times any one row to any other row. And that's going to be sort of the hardest for us to deal with. So I want to restrict us. I want to say we're only allowed to add the top row to the bottom row. So the most popular row operation, adding a multiple of one row to another row, I'm going to say we're only going to do that by adding the top row to the bottom row. To get your constant, you have to pre-multiply the top row by the constant. And then you can add the top row to the bottom row. And then we can undo our top multiplication. And then I said I only wanted to add the top row to the bottom row, and now I want to start adding the middle row to things, so I'll swap things so that that's the top row. I will multiply it by 3 to set us up for canceling out the bottom row. Add the top row and the bottom row. This one isn't going to the identity matrix, it's going to reduced row echelon form because we've got a row of zeros on the bottom. Let's switch the bottom two rows so that we can add the top row to the bottom row. We don't want to add the top row. We want to add negative 4/3 times the top row. And then we get the top row to have a 1 in the pivot column again. And then we put everything, all the rows back where we'd like them to be. And let's go ahead and do all the rearrangements at once. This would actually be 2 permutations, but we can do them at once. So let's review the row operations. This is going to be a little different from your used to because I'm tweaking row operations a little bit to make what's coming next a little bit more straightforward. We can multiply one row by a non-zero constant. We can exchange 2 rows. And for simplicity, we are going to want to say that add the top row to the bottom row rather than add any multiple of any row to any other row is our third row operation. This is a subset of the row operations you know and love from linear algebra, but it's a bit enough of a subset that you can get everything you need. Another fact worth noting about row operations, they are linear operators. So they each come with matrices. They're called elementary matrices. You might have seen them in linear algebra. So if R is a row operation, then there is a P by P matrix E such that at R of M equals E times M for any matrix M, any matrix M that it needs to have P columns. Sorry, it needs to have P rows, but it can have as many columns as you want. So this works both for square matrices M and also if M is a column vector, and we'll come back to that fact. And we call E an elementary matrix. Let's write that down because it will be nice to have a term for matrices that give you row operations. So elementary matrix just means a matrix that comes from a row operation. Now we said we can row reduce any matrix to either the identity or something in row echelon form. I don't want to get too into the weeds with row echelon form, so let's let S be the set of all P by P matrices such that the bottom row is all zeros. That includes all the row reduced echelon form matrices. So either you can row reduce to the identity or you can row reduce to something in S. There are a few other matrices in S, but we're not going to worry about that too much. Now let's put this all together. We have that if M is a P by P matrix, then we can row reduce M to some matrix L, where L is either in reduced row echelon form, meaning in particular L is in S, or L is equal to I, the P by P identity matrix, which you all know and love. So we've seen that row operation is multiplication by elementary matrices. So there are some elementary matrices, E1, E2, up through En. You multiply them all by M, then you get L. And then row reduction is reversible. If I can row reduce M to L, I can row reduce L to M. So we have that M is equal to some other elementary matrices. I'll put a twiddle on them. So we know this is maybe a different set of elementary matrices L. And these are all elementary matrices. So if A is a linear operator on RP, then A of X equals M times X is this product of elementary matrices, and then an L times X for some M, a P by P matrix, elementary matrices EJ. And L is either the identity or has a row of zeros on the bottom. But multiplying by an elementary matrix is a row operation. And also a linear operator on RP. Thus, A is equal to a composition of row operations composed with some linear operator B, where B is multiplication by L, so either B of X equals X or B of X is LX, where L is in S. So in particular, let's notice that the last row, the bottom row of L is all zeros. That means, let's give an example. we've got a bunch of zeros on the bottom. And I don't care what goes on up here. Then our top rows are going to be complicated things. But our bottom row, the only thing that can show up on the bottom is 0. So the last component, the pth component, which you can pick out by taking the inner product with taking the pth basis vector, is always going to be 0. So let's summarize what we've just seen. The most important point is that if A is a linear operator from RP to itself, then we can write A as a composition where each RK is a row operation, and B is the identity map. I'm going to keep calling it I. Or B comes from a reduced echelon matrix. And we saw in particular B has a certain property where S is the set of all linear transformations. Such that the last coordinate of B of X is always 0. And if you recall the big theorem of this video, the thing we're heading towards is proving that any linear transformation maps a Jordan domain to another Jordan domain, and you can even write down a formula relating their volume. Well, we're going to start off with rectangles. And let's let B be a linear transformation on RP, RP to RP. And it's going to be one of the following 3 things. Either B is in our set S, B is the identity function, or B is a row operation. And we've just spent a bunch of time showing that you can write any linear transformation as a composition of these 3 things. And the conclusion is that for these very basic matrices, then B applied to the rectangle is a Jordan domain, Jordan set with the volume of B of R being the determinant of B, absolute value, times the volume of R. And we will see later how to generalize this to R being an arbitrary Jordan set and B an arbitrary linear function. You do not remember anything about determinants. Here is a slightly different way to phrase the conclusion. We can say there is a constant C depending only on B, not on R, such that the volume of B of R is equal to C times V of R. And as it happens, the constant is the absolute value of the determinant, but if you've forgotten everything about determinants, we'll see there's just always going to be a constant, and then you can, if you don't want to think about determinants, you can skip the part where I explain that the constant is in fact the determinant. Now let's prove this. There are going to be 5 cases, and we'll deal with them one at a time. First case, the easiest case, let's get the easy ones out of the way first. If B is I, the identity function, then B of R is just R. All rectangles are Jordan domains. And the volume of B of R is the volume of R times 1. And then the identity function. The identity function is multiplication by the identity matrix. You may remember this is the matrix with 1 on the diagonals, 0 everywhere else. And this matrix, if you remember how to compute determinants, this matrix has determinant 1. Next, let's look at the other things you can row reduce to. If B is in our set S, then a couple of things to notice. B of R, by definition of S, this is contained in the set of all points in RP, such that the pth coordinate, that's the inner product of EP with X, is 0. So R is compact. We said the rectangles are defined to be closed. Rectangles are obviously bounded, so it's compact by the Heine-Borel theorem. B is a linear operator, so it is continuous everywhere. That is a proposition that we put up in lecture 6.5.1.3. And so B of R is compact and hence bounded. This is proposition. This is pretty much the first proposition on compactness we saw. So what's it? So put together, B of R is bounded and the last component is always 0. So there is a number m, a real number m, a positive real number m, such that B of R, it's contained in this set. Set of all points in RP such that all the coordinates are between negative m and m. You just let m be big enough, and since it's bounded, eventually you'll get there. All the coordinates up to the p minus 1th coordinate, that is. And then the last coordinate, the pth coordinate, is between 0 and 0. And the reason I'm writing it that way as between 0 and 0 is so that we can observe that the right-hand side, this set, is a rectangle with volume. Two m times 2m, p minus 1 copies of 2m times 0. And now that means B of R, you can find a rectangular cover, namely this one rectangle, such that the upper Darboux sum of, say, 1 is 0. And the lower Darboux sums are all at least 0. And that means that 1 is integrable on our right hand, on our B of R. The integral of 1 is 0. It exists and it is 0. So B of R is a Jordan set. And its volume is 0, which is a constant 0 times the volume of R. And B of X is a matrix that has nothing but zeros on the bottom. So if you remember, a matrix with a row of zeros always has determinant 0. So the determinant is our constant again. Now let's move on to the row operations, and in the interests of time, I am going to start with the row operation that is add a multiple of a row to another row, except we said we could look at just add the top row to the bottom row. This is going to be the most involved of these operators. So, which is why I wanted to simplify. I wanted to deal with just one of them. And so Let's write out what it is. It's you add the x1 coordinate to the xp coordinate, and if you happen to remember your linear algebra, this has this matrix, ones on the diagonal, zeros everywhere else, except that down in this corner we have not a 0, a 1. But this thing but that matrix, you may recall, still has determinant 1. And so now let's go ahead and show that B of R is indeed a Jordan set. So R is a rectangle, so we can write R as AB. Going to stop writing column vectors because they take up too much space on the screen. What is B of R? B of R is then just you add x1 to the last coordinate. All right, now we're going to use some results we know. Let's let S be the rectangle at the base. I'll go ahead and use Y's instead of X's. And if you think about it, you can see that B of R, this is the set of all pairs YT, such that Y is in our rectangle S, and then T is our X coordinate, it's XP plus X1, so XP is just T minus Y1. And we can write it, we can move the Y1 over. All right, and now notice that the function that's a constant plus y1 is continuous. So we have that by the big proposition from the last lecture. B of R is Jordan. Computing the volume is somewhat tedious, so I think what I will do is I will just draw the picture that lets you compute the volume, and working out the somewhat messy algebraic details, we'll leave that as an exam study problem. So here is a sketch of the y1 t-plane. Then y1 is between A1 and AP, and sorry, not AP, B1. Then we've got AP plus A1 up to BP plus B1, and we end up with this parallelogram. And then we've got AP E plus And we've also got AP plus B1 and BP plus A1 here. These last two are not necessarily in that order. They might come in the other order. Then what we do is we're going to take this rectangular cover. We're going to split this up into a bunch of skinny rectangles down here. We take the following rectangular cover. We'll need 3 rectangles going along each way here. And then the 2, 3, 4 up through P minus 1 coordinates are coming straight up, straight out of the board, out of the screen, because this is basically a cross section, and all the cross sections are the same shape. And so we indeed have, if there are n little rectangles down here, if this is B1 minus A1 over n, so there are n rectangles, you can see that we've got that these rectangles are contained in our B of R, and then you throw in the ones at the edge, and you're covering B of R. And if you do the algebra, you can determine that the upper sum of 1 over this partition is the volume of R plus B1 minus A1 squared over n. If B1 minus A1 is 0, then the volume of R is 0, and the volume of B of R is also 0. Otherwise, lower sum comes out to the volume of R minus B1 minus A1 squared over n, if n is large enough. And then taking the limit as n goes to infinity, we see that, the volume of B of R is the volume of R times 1, and 1 is just the determinant of B. And I think I will go ahead and leave it as an exam study problem. If B is one of the other 2 row operations, that is, if B switches 2 rows, or multiplies a row by a constant, I'll leave it as an exam study problem that then B of R is, in those 2 cases, in fact, it is a rectangle, so there's no worries about whether or not it's a Jordan domain, with the volume of B of R equaling the absolute value of the determinant of B times the volume of R. And those two are the ones where the determinant might not be 0 or 1, so you get a slightly more interesting constant, but on the other hand, you get just a rectangle. And that is all there is to that.